So we've been working on patterns that multiply to get from one term to the other. And so what I wanted to do is look at an example of when those patterns get added up together. So this is similar to when we studied arithmetic sequences and we wanted to add up all the arithmetic terms. And we had this special formula that we used for the sum of the first however many terms of an arithmetic sequence. So let's try with an example. My favorite example of a term is looking at these different triangles. So adding up how many triangles there are. And so you can see that at each stage, this is called Sierpinski's triangle. And you can also see I'm not an art teacher, but at each stage, the size of the triangle gets smaller and the number of triangles also gets bigger. Okay, so the more triangles there are, the smaller they get. And so what I'm going to do is I'm going to count the number of upside down triangles in each one here. So we'll call this n equals 1, and we'll say that there is one upside down triangle. In this one here, there are, um, actually, let's count the right side up triangles because that they stay the same size. I'm changing my mind. We could do the upside down triangles as well. Maybe we'll look at that in a second. So we have in n equals 1, we have 3 of the right side up triangles. I'm not counting the outer shape, just 3 of that small size. In n equals 2, how many of the right side up triangles do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 triangles. And then here, that same pattern repeats. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the same 9 over here, the same 9 over here. So we have 3 times as many more, 27 right side up triangles. And so what I'm noticing is that the value of the number of triangles is multiplied by 3 over and over and over again. And so the number of triangles has this pattern. Let's say that the number of triangles at step n starts with 3 and it multiplies by 3 over and over again. And the n minus 1 is because when we get to n equals 2, we've only done one multiplication. That's 2 minus 1 copies of 3. When n is 3, we've done 2 multiplications. So that's to the second power. So what I want to do now is add up all of those terms. So the sum of the first 3 terms. What we can do is we can write out 3 plus 9 plus 27. Of course, you can go through and just add that up directly, but if I wanted to do, say, the sum of the first 50 terms, that strategy of adding them all up would no longer be super efficient. So what I want you to notice is that each of these terms has a 3 in common. And each of the terms left over on the inside can be written in terms of the R value, what we multiplied by. So 1 plus 3 to the first plus 3 to the second. Okay. So what I'm going to do is I'm going to do a little trick here. I'm going to try to cancel some stuff out. Because right now I have 3 different terms and I want fewer than 3 terms. So I'm going to take that whole thing that I just had and I'm going to multiply it by 3. 3 copies of the sum. And I'm going to distribute it inside. So 3, and then I'm going to distribute. So 3 times 1, 3 times 3 to the first, 3 times 3 to the second. So what I did was I took this 3 here and I multiplied it by 1. I multiplied it by 3 to the first. I multiplied it by 3 to the second. I just distributed it into the parentheses. What I'm going to do next is I'm going to write my original S3 underneath it. 3 times 1 plus 3 to the first plus 3 to the second. And the idea here is that there's a lot of things that cancel out. There's a lot of things that match up. Like you may notice that this matches with this, and this matches with this, and even this part matches with that part. So if I subtract these two sums from each other, what I end up with is this. 3 minus 1. How many are left over? 3 minus 1 means there's only 2 copies left over. Both of them had this 3 in common, so I can pull that out in front. And on the inside of the parentheses, 3 to the first minus 3 to the first is 0. 3 to the second minus 3 to the second is 0. I have 3 to the third minus 1. And that means that the thing I actually care about, S3, I can get by just dividing by 2. 3 times 3 to the 3 minus 1 over 2. If you actually want me to go through and calculate that, I'd go 3 times 27 minus 1 over 2, which is 3 times 26 over 2. 3 times 13 is 39. Now you might be wondering, that is a whole heck of a lot harder than just adding up 3 plus 9 plus 27. But what I'm going to do now is show you that this exact same idea works no matter how many terms I want to have. So I had terms that looked like this, 3 times 3 to the n minus 1. Let's say I wanted to add up the first 50 terms. Well, what did the first 50 terms look like? 3 plus 9 plus 27 plus a whole bunch of junk. And the 50th term looks like this, 3 plus 3 to the 49. Because when you plug in 50, you take away 1 up here. All right, that's a lot of terms. I'm not going to add that up. What I'm going to do is multiply it all by 3. 3 times S50 is going to be 9 plus 27 plus a bunch of terms I don't care about plus 3 times 3 to the 50. All of those terms have a 3 in common. So I can pull it out and write my terms like this now. My original one was 3 times 1 plus 3 plus 9 plus 3 to the 49. All of these terms have a 3 in common, times 3 plus 9 plus blah, 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 plus 3 to the 50. Notice what matches up. Factor that common thing out, cancel, 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 and the 49 cancels as well. So if I subtract these two terms over here, I have 2 S50s left over, and over here I have 3 times 3 to the 50 minus 1, which means my S50 is 3 times 3 to the 50 minus 1 over 2. Now that's a huge number. I'm not even going to write it down because, well, let's see if the calculator can even do it. We might overflow here. But it's good to know how you would type it in, I suppose. Okay, so our calculator handled it, but it said E24. So remember, that means move the decimal 24 times over. It's a big, big, big number. In general, I'll show you the general formula, but it's the same idea that if you multiply by r, it shifts all your terms over by 1, and so everything cancels out. So let's say that we had a sequence like this, where it starts with the first term times a ratio to the n minus 1. If I want to add up n terms, I'm going to do this. Oops, I wrote that wrong. The first term is just t1. The second one is t1 times r. The third one is t1 times r squared, ... The last one is t1 times r to the n minus 1. Really hard to know what to do with all those terms that you don't know. So if you multiply everything times r, you get t1 times r plus t1 times r squared plus all those same terms, just with the power up by 1. If you start looking for things that cancel out, this matches this matches this, the dot 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 eats all of those. And so if you subtract them from each other, the bottom one minus the top one, you have t1 times r to the n minus t1. Or like I showed you in the other version, they have the 3 in common. They have that first term in common. If I think about what the left side has in common, the left side has an Sn in common. And so if I want to get the sum I actually care about, I divide by r minus 1. And that's your general formula. So I did an example with the triangles where you could count them up, where it started with a 3, so the t1 was 3, and it grew by a factor of 3 over and over again. And you can see why we were dividing by 2, because that's 3 minus 1. In general, you're going to have your general formula. I didn't mean to delete it, but your general formula is the first term, common ratio to the nth minus 1, divided by the common ratio minus 1. So there you go. Let me know what was confusing. Happy to help out.